Hi. When we're talking about volumes, there is a particular case that is going to be very easy to calculate in terms of mathematics, and that is the solid of revolution. That happens when you have a function that you can graph in a two-dimensional plane, and then take that function graph and just turn it around a certain axis, revolve that region above a line. That way, we're going to obtain a solid of revolution. And notice that because we are getting that solid of revolution, it's going to be very easy to quantify the volume in terms of calculating the areas on the particular interval where the function was defined. And this can be either on terms of the variable x or in terms of the variable y. Because we are revolving around, it's very easy to think of this as the cross section as a disk, and then we're gonna find that once the radius of that disk is in terms of x and or y, the cross sectional area of that disk is gonna be just pi by the radius square. So it's very easy to find that particular area. Notice that this is the situation. We have an area that is given by one curve or maybe two, and then we're going to have this axis that's going to be the axis of revolution. So the cross section here is what we call a washer because it's between two discs and it resembles like a washer. So this washer is going to have two radius. It's going to have an internal radius or an external radius. And it's accounted by the radius of the outer part of the washer and the radius of the internal part of the washer. And so notice that this is what happens. We have this area, and this area we turn it around this axis, and then we get this volume. Notice that when we get that volume, then we have a disk here, and this disk here in red is representing the volume that we want to check. This is a cross-sectional piece, and that cross-sectional piece, we can find the area by calculating the difference between the two circles. So the difference between the big circle, which is going to be given in area by pi outer radius square, minus the difference of the inner circle, which is going to be given by pi inner radius square. Now, once we have this, then it's just a matter of, then again, integrating the areas. So one of the big things here is to be able to identify who's the internal and the external radius. So let's see this with an example. Let's see how to find the volume of a solid by rotating a region around the line x equals -1. Now notice that this figure here is giving me the region between the function y equals x, or if you want, x equals y, and the function x equals the square root of y, because there's no particular reason why we have to do in one variable or the other. The method might change, but we can definitely work with the variable that is more comfortable for us to do with respect to the axis of revolution. So now here, notice that this is what's happening. This is the area that we want, and we're turning this around, and so this is forming a solid. But we now want to calculate first the area of this disk, this ring that we have over here. So we have, of course, the internal and the external radius, and then we can account for those. So using, first is going to establish the formula of pi outer radius square minus pi inner radius square. And then we're going to calculate what that radius is. Notice that the radius is going to be the distance from this point, from -1 to the function. So if the function is here x square root of y, which is the outer radius, then it's going to be a square root of y distance to -1. So this is going to be a square root of y minus -1. That's how you calculate the distance, the difference between those two values. So that's why it's going to end up being 1 plus the square root of y. And for the function y, then it's simply going to be 1 plus y. Remember, the line is x equals minus 1, which is this. So to calculate the distance, you need to subtract both of those things. You need to subtract x equals minus 1 and x equals y. So that will be y minus 1. So that will be y plus 1. So that gives me the radius here, the second radius, the inner radius, and this will be the area of this cross-sectional piece. But now, of course, because we want to do this in general, now then we do the volume. And notice that we're going from 0 to 1, since this is where they two cross. This starts at 0, and then they cross again at 1. That's where the function square root of y and y are equal. And so, and those 2 points are going to be the limits of my integral. And then once I set up this in the integration, I need to break apart the binomial square that I have for both of these things. So remember, the first square times plus 2 times the first term, which is 1 by the second, plus the second square, which will be y. And then I gotta break this one as well. So once that I do this algebra, I'm going to obtain that this is 2 square root of y minus y squared. And once that I integrate that, normally, this is integration by powers. This is 4/3 of y to the 3/2 minus y squared over 2 minus y cubed over 3. That between 0 and 1 multiplied by pi. So that will give me pi half. All right, so that was an example of using that, but one of the important things here is always analyzing the cross-sectional area. So now let's talk about finding volumes by using the cross-sectional area. Now, to find the volumes of the solids that are not solids of revolution, but they have cross-sections, we can kind of do that by finding what the cross-section in each case is. So for example, here in this figure, we have a solid with a circular base of radius 1, and parallel cross-sections are going to be perpendicular to the base. They're going to be equilateral triangles. So we want to find the volume of this solid. So this is the picture of what this is. Notice that each of the cross sections is going to give me a triangle. So let's look at this and how it looks in the plane. So if we take the circle to be x squared plus y squared equals 1, so the base of this figure, we're going to have this below looking like this. Now, a typical cross-section at distance x from the origin is going to be shown in here. And notice that this is the base, and we can define y to be a square root of 1 minus x squared, put in y in terms of x. And here we have the triangle that is defining the cross-section. And so if we're assuming that this is working in this way, since it's an equilateral triangle, all the sides are going to be the same. And also all the angles are going to be the same. So this is 60, 60, and this angle is also going to be 60. Because for finding the area of a triangle, I need base by height divided by 2. Then I'm going to define each of the sides of, I'm going to draw this height over here, which is going to split down the middle, the base, and I'm going to call each piece of the base y. So this is going to end up being a base 2y. And if I do that, doing a little bit of trigonometry, I'm going to find out that the height is square root of 3y. I'll leave that calculation to you to complete, but essentially with a little bit of trigonometry, you can do that using the fact that this is a 60 degrees angle. Now, since we have the point lies in the circle, then we have that y is equals 1 minus x squared, and so the base of the triangle that is in terms of y can be seen as 2y or 2 1 minus x squared. Now, since the triangle is equilateral, then the height is square root of 3y, and we're just going to have a square root of 3 1 minus x squared. So now, remember, the area of a triangle is base by height divided by 2. So we have here all the components. We have 1/2 of the base times the height. And so that's going to give us that the area of the cross-sectional here is a square root of 3 1 minus x squared. This is something that we always want to do. We always want to try to express our areas in terms of a single function. Now, once that we have that, then the volume is much more simple. Then we just calculate the integral to sum all the areas. Over here, as you can see, this is just powers. And so this ends up being square root of 3 to square root of 3 x minus x cubed divided by 3. And this is going to give me 4 square root of 3 over 3. Now, this particular solid with cross-sectional area can be a little bit of complicated to replicate depending on whatever your solid is. So we want to grasp very specific ways of finding those volumes. So now we're going to discuss two different methods for doing that, which is going to be the method of cylinders and also the method of washers.